Hello everybody, my name is CHRISTOFOROS KOLYVAS. I'm from Greece and I'm representing FIFE in Europe and Middle East. So FIFE is recently acquired by a bigger corporation called Aegeon Corporation. We're under now the hood of Aegeon. Aegeon mostly offers solutions for the infrastructure projects and with a great focus in pipelines. However, FIFE and FIBRAP are the companies inside the team that will introduce also solutions for other type of infrastructure projects apart from pipes. The type of FIBRAP systems. The type of FIBRAP systems was actually developed by FIFE back in 1988. FIFE is the company manufacturing and developing these systems in order to give solutions for reinforced concrete structures as well as steel and masonry structures. It all started, as I said, in 1988 from Mr. Edward Fife, that's the founder of the company. And actually the main goal was to strengthen the bridges of Caltrans, of the California Transportation Institute. After that, there are thousands of projects all around the globe, both in buildings, bridges, and other type of infrastructure projects like pipes. Blast mitigation is also a big part of our projects, and industrial structures overall. We can easily say that it is nowadays the most approved system in the world. We have approvals in the United States, obviously, especially the ICC, the International Code Council approval. We have approvals in Germany by DABT. We have approval here in France, and Avitechnique. Obviously, our epoxies are CE certified for use in Europe, in the European Union, and the same exact system with the same properties and the same epoxy is also approved in Australia, in New Zealand, and all over Asia. As I said, we started with, and I will show afterwards, we started with research. We were more or less, we consider ourselves pioneers in the field of FRP strengthening, of structural strengthening by means of FRP. Afterwards, a lot of research followed. We have really strong connection with the academia. We more or less, we were on the wave of the FRP development, so the company was evolving in parallel with the technology actually. So most of these tests that were the first ones in the field of FRP structural strengthening was done with our systems. We have now thousands of test reports. Some of them obviously are now outdated since they are newer and more evolved reports after them. We also participate in committees. We participate also in the CSTB committee, in the FGC committee for the new guideline that you saw also in the box. It was given to everybody. It's the new guideline in France for seismic strengthening with fiber reinforced polymers. And this is the first test that was done for Caltrans. It was done in the University of California in San Diego back in 1988. The demand back then was to actually have a very rapid way to strengthen bridge piers after the event of an earthquake. I was not present, obviously, at this type of test since I'm a lot younger. But what I have heard it was that Caltrans actually was investigating back then to have like prefabricated steel jackets ready for the event to really go and install them just after the earthquake so that they prevent collapse from a second earthquake. And then the idea came up to wrap these columns actually with materials that up to then it was mainly used in the aerospace industry, and to introduce in this type of structures. So this was the first test. It is a large-scale specimen of a bridge pier. It was laterally load applied laterally until it failed. You can see here exactly the shear force versus displacement diagram. Then the same column was repaired and wrapped with an aramid glass type of fiber reinforced polymer back then. You can see the advanced loops and actually the deformability that this column had. This is one of the first tests that showed what we say the ductility enhancement, so the capacity of the column to deform more without failing when it is wrapped with a fiber reinforced polymer jacket. So more or less this is how everything started. After that, a lot of strengthening took place. This is one of the first bridge pier strengthening with FRP. It is in Los Angeles. It was back in 1991. 15 piers of 10 meters tall were strengthened. And apart from the testing that we see in the laboratories, this type of old wrapped structures has also tested by Mother Nature. So the well-known Northridge earthquake followed. That was really close. The epicenter of the earthquake from this column was close to 14 kilometers close from these piers. And here you can see the founder back then of the company, Edward Fife, going there with a newspaper from the earthquake, showing that the pier is there and it's standing and everything is okay. We continued obviously with seismic upgrade for improving the ductility of reinforced concrete columns. Thousands of columns are wrapped in this way, either with carbon fiber reinforced polymers but also with glass fiber reinforced polymers. Glass fiber reinforced polymer is a good solution for seismic strengthening, since glass fibers can deform by far more than carbon fibers. They don't have the same strength capacity. But in the case that we just need to wrap for ductility, we need this elongation, and there is also the main advantage that they are by far more cost effective than carbon fiber reinforced polymers. Here you can see also some wrapping application of bridge piers. Apart from the ductility enhancement, other type of actually strengthening of members was investigated, adding to the capacity. So here we see more like RC columns with high aspect ratio or wall-like or shear walls that they take a lot of shear and acting on them during the event of an earthquake. So here the application is in order to increase the shear strength of the structure by adding actually more hoop reinforcement around the element. This is also a type of application like that. This is for strengthening of a bridge pier at its base, where most of the shear action can be found during the event of an earthquake. Also, this is a bridge pier that an earthquake, cannot recall which one, but an earthquake passed afterwards, and still we have a satisfactory result. Now I want to talk a bit about the Tylo composite anchors. Fife is more or less the inventor of this type of system. It is an obvious way to move the stresses from the wrap inside the concrete or through obstacles. We use it to go through walls. We use it to strengthen a U-wrap of beams, as you can see here. We even use it. First of all, this is tested. It's tested also here in Lyon. In order to be involved in the Avitechnique approval. We can use it even to wrap around beams. This is a case where we actually increase the ductility, the deformability of the beam, but since obviously all the beams they have the slab, we need to go through. So this is a way that with a full wrap with Tylo anchors, you see they are passing from the top, they come down, they open, and then also a U-wrap follows. So like that we can fully wrap actually the beam. Another application of anchors here is for shear strengthening of bridge piers. Bridge piers with a nice shape that includes angles that may debond the system when the whole system is the beam is under load and the FRP jacket is activated. So the anchors here are used in order to connect the two sides and to prevent debonding. We're talking about through anchors in this case. Another interesting case is strengthening of columns into the foundation. This is a testing completed in the University of Patras with Professor Tretafilou. Obviously it was a seismic test with lateral deformations. We investigated various types of anchors and configurations, including fiber optics to see exactly the strain deformation inside the anchor. A project based on that just followed. This is a water reservoir in Saudi Arabia. It had around 1,600 columns inside. Saudi Arabia in the area of Jeddah actually has a slight seismicity, and especially for so important structures like a water reservoir in Saudi Arabia, they need to have, for the possibility of an earthquake that will come in 1,000 years, they need to have this type of important structures strengthened. So all these columns needed to be strengthened. The initial detail was actually to apply a new concrete jacket that obviously will decrease significantly the capacity of the reservoir. We came with an alternative, and we gave the solution of wrapping the elements for having both the flexural strengthening required by using the Tylo anchors inside the foundation, but also in the top at the slab, as well as wrapping around in order to increase shear and in parallel obviously increase the ductility at these areas where the plastic hinges are about to be formed. Another interesting project with the use of anchors is in Lima, in Peru. This is a bridge that had both circular columns and also wall-like columns, as you can see here in these pictures. This is the case of the circular column that was wrapped around in order to increase its ductility. This is a very straightforward application, and you can see here some pictures of it. Most interesting is this application of this wall-like column. You can see here that due to the bending expected after the earthquake, flexural strengthening at the base was required, and Tylo anchors were again used in order to pass all the forces into the foundation. You can see the details here, and here you can see also part of this application. Another interesting application, again in Latin America, was in Chile in Lautaro bridge back in 2010. This is the case of a repair of a bridge after the event of an earthquake. There was a very big earthquake, very close to the epicenter was this bridge. Unfortunately, this bridge also had a construction error from the beginning. So the shear links, instead of being outside the vertical bars, the main reinforcement, they were inside. So obviously there was the local buckling of the reinforcement. This is one of the main issues that we face with existing structures against earthquake, is that there are a lot of construction errors and poor details, as also Mauricio mentioned before, either because of old codes or because of construction errors, as I said, that create the problem. Then there was obviously also the failure at the base from the bending moment that was a result of the earthquake action. So the solution was to increase, obviously to repair all these damages, to increase the bending capacity of this section, and also wrap around in order to prevent a future buckling of the main reinforcement. Here there are some pictures of this, some photos of this project and the wrap that was done around, obviously following the repair of the spalt concrete. Finally, I want to talk briefly about the possibility for seismic strengthening of masonry structures. Masonry structures that in some cases were not allowed to use epoxy-based systems, since there is no compatibility of epoxy with old masonry, and especially with historical structures. Moreover, there is not a mechanical compatibility, since we're talking about, in the epoxy-based systems, about a very strong system compared to the strength of masonry. Masonry is a structure that works well under compression, but does not have more or less any tensile capacity. So offering some tensile capacity to the structure in some cases is more than enough in order to strengthen against seismic action. There was a big program that we carried out for the development of this type of system back in 2005, followed with a lot of research, again with Professor Triantafylou in the University of Patras, forming a guideline to design the system, and also testing the mechanical properties of the system in the form of coupons, more or less how we do it with the epoxy-based systems. Obviously, with this we can strengthen masonry for in-plane actions as well as for out-of-plane actions. We can wrap around, as you can see at the top corner, the top of the structure in order to prevent overturning of walls. This is the coupon testing that we did. We wanted to identify exactly the mechanical properties of the combination of the fabric and the mortar. You can see here that epoxy is changed to mortar. This is the difference. And instead of using dense fabrics, we use an open weaved fabric system that interlocks with the mortar. So this is how the system is, and everything is bonded with a repair mortar on the structure. So here are the coupons that we did in order to identify the mechanical properties of this system, and some further testing. This was done in Turkey with Professor Ilki. This is for shear strengthening of masonry walls. There were old bricks from 100-year-old structure in typical structure, Turkish structure used in order to build the walls and really simulate how old walls were. And the system, the reinforced masonry system, was applied at both sides of the wall. Debonding was the main failure, and that's why also here typho anchors were examined in order to keep the system in place with very satisfactory results. That's it for me. Just a brief introduction in the overall technology and some projects that I showed. And thank you very much for your attention.